So thanks everybody for coming to this rather early session. I'm Joël Falcou. I will be co-hosting this talk with Denis Yaroshevskiy. And we will be speaking about how to do SIMD programming in the new world of C++20 and how we actually manage to do that. So for those people following along at home, you can actually follow on the slide using these links, also the ones that we actually put up in the chat. So you can actually look at the slide yourself if you want to get into details or whatever. So let's get directly into the meat of this talk. If we are speaking about SIMD programming, is probably because we want to do some performance. And let's try to see what kind of performance we are speaking of, looking at some basic benchmark and try to understand what is going on. So let's say you want to find a bunch of values in an array. This array is about 1,000 bytes, depending on the type you are dealing with. This is char, short, and integers. You will get some kind of different timings ranging from 72 nanoseconds for int, 128 for shorts, and about 240 for char. And this is what you get when you run regular std find if algorithms using the bare bone elements. What we propose is a way to get that much faster using this version of the code, where we basically stay around 8 point something nanosecond, depending on the types, which led us to a speed up of about 9 on integers, roughly 16, probably 16, a little bit less than 16 for short, and around 32 for char. So there is a lot of performances we can actually fetch from even this simple code. But we can say, yeah, okay, fine. We're doing a find if, which is somehow a simple operation. So maybe, we get some speed up, but what tells us that we are actually going at the right speed? Well, the thing is, there is a version of find that we use quite a lot, which is actually strlen. So strlen is basically seeking a 0 in an array of bytes. And if we compare what we did to handwritten, the well-handwritten and optimized strlen, we basically see that we are in the same hotspot of a few 8 to 7 nanoseconds, knowing that strlen is actually something that compiler vendors or library developers optimize quite a lot with whatever tricks they can find. So we are basically at the level of strlen in terms of speed, except we use a higher level form of abstractions. And just to be clear, there is actually one thread running there. There is no multi-threading. It's pure optimization at the SIMD level. And every bench we will be speaking about will be single-threaded. So, okay, so it happens we can vectorize a find if, which can be seen as a very easy function to vectorize. What about something more complex, like, I don't know, inclusive scan? So inclusive scan, it's basically something that do a generalized partial sum. It's a bit more complicated, especially in parallel, because you need to find a way to propagate these partial sum at each blocks. So we get, again, some timing with this array of 1,000 bytes, ranging from 205, let's say, for char, 123 for short, 69 for int. And then again, we can actually write something faster than going there. And so in this case, we got a speed up of about, let's say, about 2, okay, for integers, about, let's say, slightly less than 3, 2 point something for shorts, and a speed up of 4 for char. So it's more complicated, but we get speed ups. So we can actually vectorize complex things if you want to do it. Okay, but it's still something, like, data goes in, data goes out. It's very regular. Can we do better? The thing is, what about remove if? So let's say you bench remove if, and you graph the time spent to do a remove if of, let's say, all the zeros in an array of values. And what you do is that you bench this remove if with respect to the percentage of value you want to remove. So it happens that you get this very nice symmetric graph where if you have nothing to remove or everything to remove in your array, so it's full of zero or there is no zero, you will be probably playing really nice with your branch predictors, and you get a very fast operation of around, like some thousands nanoseconds there, and probably around the same there. And you have this like curve bell there that's a peak at 50%, because at 50% of value to keep, value to remove, you will be probably just jiggling your branch predictor too much. And we go up to 25,000 nanoseconds for char, 8,000 for short, and 1.4 something for int. But remove if sounds like clearly something you cannot vectorize because you are moving data around. It's very complicated. The trick is actually you can actually vectorize that. And let's focus on char. We get this very flat graph because when vectorizing this kind of operation, you remove all the branches. So the branch predictor doesn't take any toll on your performances. And you get this very flat 1,000 something, nanoseconds. So that gives us a speed up of 4 or 2 in the worst case, let's say. And in the worst case for the scalar version, we are basically 25 times faster. And the same scenario we repeat for all the types. And the maximum speed up for short being around a bit more than 10. And for int, which is the worst case actually, it goes from basically 1 point something to 3 times faster. So we can actually vectorize complex operation. And we will have to remember that all of this, single core, just vectorized operation, are actually something we can manage to do. So the question is, how do we get there? Okay, so that was a bit of a flashback things, but how can we actually get there? And so to do so, we designed a library which is called Eve, that help us actually write those kind of things and a bit more. And what we'll be doing is looking at how these things works. So let's dive into it. So a quick refresher for people that may or may not actually at ease with the SIMD process. So a regular operation on the CPU is actually run in a way that you get a flow of instructions that get applied to a flow of data. And every cycle, some instruction is started, to work on some data. And somehow you get a result from another instruction at the same cycle. So you get this flow of operation going on there. And what SIMD does, it just say, okay, let's keep this model with a single instruction flow, but make it so the data we work on are actually multiple of them at each cycles. It can be a block of 2, a block of 4, 8, 16, up to maybe 64 at a time, depending on the type and the size of these very special registers. And every time an instruction is fired, it will work on this block, this pack of data, something that we usually call a wide register. And the output we get is also a wide register of multiple values. And if everything goes right, we expect to get some kind of speed up related to the width, to the number of lane into this register. All again in the single core. So there is this kinda untapped things that we need to put forward. And the question is why is it an issue? Well, it's an issue mainly because there is I don't know how many variants of those kind of instruction sets. If we focus on x86, we have 3 sizes of wide register, 128 up to 512 bits. For each of them, you have multiple, up to a dozen of instruction set variants. And up to a certain point, they are all backward compatible. So if you have a machine with SSE4, you can use whatever comes before. Same for AVX. It gets trickier with AVX 512 because the layout of the instruction set doesn't make sense, but that's another story. So if we focus on x86, we already have a lot of things to consider and to choose from, and we will see that it's not that trivial. But God forbid you actually need to write a code that use SIMD instruction on multiple different architectures, because I don't know, your application has to run on a PC and on a phone with the ARM processors. Well, then you can add all the variants of the ARM instruction set. And if you are into supercomputing, you can also add all the specificities of PowerPC and so on. So you cannot actually just go into that and expect to be efficient right off the top. So the question is, how can I actually exploit that? Is there any tools that help me? There is a bunch that are supposed to help us. But first, the question is, do we care? Do we care about selecting those architectures? The fact is, in fact, we do. So if we compare the runtime between the scalar version in orange there and all the other one, we see that in all cases, whatever the instruction set we select, is it SSE4, is it SSE2, is it AVX2, we get some speed up. But we see that the speed up depends on the architectures we are targeting for. So this selection is actually primordial, and you need to be aware of the target architecture you want to write your code for. So it's not that we can just pick one and be happy and we can forget all the others. It has to be taken into consideration rather early in the development process. What can we do? Well, it sounds like it's a compiler problem. I mean, generating instruction for this or that architectures probably an issue for compilers. So what about looking at what compilers can actually auto-vectorize? They can actually vectorize quite well in some situation, but as soon as you go out of the, let's say, transform or transform reduce pattern on regular function and operators on regular types, it starts to be complicated, and you will be at the mercy of the quality of implementation of the auto-vectorizer. It's a worthy technology, but you have to adhere to those strict restrictions. Well, maybe I can get some more leeway by using special pragma, maybe OpenMP, SIMD or something, or some Intel-specific things, or some very specific compilers. You can, but then again, they all come with the caveat that you need to follow some kind of patterns. And if you are going out of that, well, it doesn't work. And one way to see that in action is that we actually get a speed up of all those benchmarks, mostly because the auto-vectorizer doesn't know how to treat findIF or removeIF or inclusive scan. So it just doesn't do anything. But, well, when it works quite well. Maybe you have like standard or standard-like libraries that give you something, but most of the time they are tied to the quality of the compiler auto-vectorization. Maybe you have the change that your actual task is actually already vectorized by someone that took care of that, but that means that you have to be into the exact use case of those library, like SIMD, JSON or Allied or whatever. And if you're not, well, again, you're basically on your own and you have to write this kind of code by hand. The caveat is you don't want to do that. You don't want to write stuff by hand. It's complicated. It's rather obscure. The API makes no sense most of the time, and it dilutes the algorithmic part of your code into arcane invocation. So what do we propose? Eve is supposed to simplify that. It starts like a classical, classical wrapper around the SIMD intrinsics. But we wanted to do more. So yeah, we provide something that shield you from actually writing intrinsic by hand. We have a library of code types that do just that. So you can actually write portable code with no issue with respect to the architectures, and you got operators on that, and you get a lot of functions on that. But we also provide algorithms, more like standard algorithms, and we also provide reusable algorithmic blocks. So instead of first just having the ready-to-use cookie cutter algorithms, we have a set of concepts and objects and functions that help you actually combine them or build your own algorithm with your own specificities. All again within the the level of abstraction we need to assess the SIMD instruction set below. And so we have a bunch of numerical functions, because usually what you want to do with all those things is computing things that range from basic operators, libc-like math, like trigonometry or square root or whatever, to some kind of more advanced math like special function, Bessel things, random number probability distribution and whatnot. We like math. So that's the core of the things. And it actually works on all x86 flavors and on the 64-byte ARM architectures. And by support, we mean that it's tested and it's actually maintained actively. We have work in progress for PowerPC and ARM v7 things. The code is there. It's less tested for architectural resource reasons, but we are getting there. And it's MIT licensed, so it's rather permissive on this front. So what's going on with this? What do you need to do with that? We need C++ compliant, C++20 compliant compilers, both on the compiler side and the standard library side, because we need a lot of concepts and bit manipulation functions. So that means that we probably tell you that to use the latest Clang or GCC, and by latest we mean the latest. We have this ambition to keep surfing on the advance of compilers so we can actually get the most out of them at each time. For people using MSVC, we are doing some work on that. The MSVC Clang thing starts to want to work. It's almost complete. The MSVC version is a bit more complicated because we have a divergence of opinion on what is an actual C++20 compliant. But that's something we are working on, and we are trying to get there. So let's have a look at what's going on inside. So the classical thing is we have these wide types that we just represent a wide register, so you can actually put stuff in it. You can put a constant. You can build it from a lambda that will fill all the lanes. We will see later, but obviously you can load data from memory inside the wide. The wide takes two parameters: the type and the size of the wide registers. And by default, the size you have is the largest size possible for your architectures. So once you have that, you can actually pass them to a bunch of operators. You can print them. You can call operator on them. You can call functions. We'll be going back on that. And there's a simple example. So this is the SCC 4.2 version. So when you are compiling for SCC 4, your wide of float contains 4 elements. So you get your 4 elements, you get your results, and so on. And when you compile for FX2, you have like twice as much as expected. So we have this current API thing that you can use to know which kind of API you are currently dealing with. And the one thing interesting is there is this call to this rather peculiar function, this quarter cycle f of cost. So this is something we are quite actually interested in. When you look at most of the SIMD wrappers, at some point you need to see that there is a choice to make between going fast, being precise, taking care of corner cases, and all of these options are complicated. And we didn't want it to force a choice on our users. So you can actually call costs directly, it works, but it will try to find the best way to do your cossiness depending on the range of your input. And what we do there actually is that we can say, yeah, you know, I actually know that my range of values coming in this function is more restricted than usual. It fits into a quarter of the unit circle between -p/4 to p/4. So I want to say the libraries that I know that in advance. So we have this notion of function decoration. All our functions are actually callable objects. That means that we can pass them to other function or other callable objects, and we get back another object with a slightly modified semantic. So the quarter circle is the fastest trigonometric cases because most of the trigonometric function is a polynomial approximation on top of a reduction of the angle towards the quarter circle. So if we look at what we do there, this is the ARM64 cases, by the way, we end up with a bunch of FMLA, comparison, multiplication, and dot. It's very terse. We have everything between that and the full circle one. We have half circle, we have full circle. And this is the difference if we go full-blown costs. So we are having something like 60 lines. And there, it's a bit more complicated. You see that there is a lot more cases that need to be taken into account. It's still fast, because if we try to find the fastest branch if possible, but it's slightly less faster than the one that you know about. So we have a lot of decorators that let us do those choices. And that help us actually having a better API on that and a better user experiences. So, as I said, F is a C++20 library. And so let's have a look at what we do. I mean, the main elements we are using from C++20 and C++17 are concepts and if context first. So I will just dive into the detail of one function, so we can actually have a look at that. So let's have a look at the internal implementation of the x86 absolute value functions. Basically, what we do is we have a bunch of concepts that let us overload functions on the property of types at the mathematical level. That's what we do there with this kind of concept. So we can actually triage between floating point, integers, signed values, etc. But at the math level, not the language level. That's a classical use of concepts. And one other thing we do is that we have a way to compute what we call the SIMD ABI of a wide register, which is given a type and a number of lengths, a cardinal, a size of the wide registers, we can compute the best architectural target we can use. That's what we call the SIMD ABI. And SIMD ABI are models of a given concept that we can check with this x86 ABI, which is one of the multiple concepts we have between this ARM ABI, PPC ABI, emulation ABI. So we can actually directly overload a function on the kind of architectures we need to take care. So basically, we just jump into the x86 as soon as we know that we are dealing with the x86 compatible type. And when we are inside this function, the other cool things that we bring from C++17 and 20 is that the code itself is basically a web of if constructors that will enumerate the property of the types and generate the proper code depending on the types, depending on the architectures, and depending on the choice of the users in terms of speed of accuracy. So there we just go down and get all the variants of ABS that we can get, including the specific architectures, things that only triggers after a while, and so on. And we do that so we are sure that we can capture all optimization opportunities from within the hardware. And most of the functions just look like that. The concept helps us a lot there, and will also help us a lot on the algorithmic front, which is exactly what Denis will be speaking right now. So I'm ending up over to you, Denis.
Hi everybody. Hopefully you can see me. And now let's hope that this will work. Thanks, Joel. So I'm going to talk about our algorithmic library. There was a question in the chat about like, hey, how are you different from the other libraries like this? They're great, but we do algorithms. And as far as I know, they don't for most part. Let's have a look. So what we have out of the box, we have all of, any of, none of. We have find ifs. We have equal, mismatch, transform in place, transform to. Right, so in the standard, if you look at it, like you have standard transform that just accepts an output parameter. However, we can be slightly more efficient if we know we write to the same array as we read from. This is why we have two versions of those. All right, we have reduce. We have inclusive scan in place, inclusive scan to, which is the same idea as transform. So you can do in place or you can do to some other range. And we have remove and remove if with a slight caveat. I didn't finish AVX 512 yet. Okay. So let's have a look at some of the basic algorithms, right? So we have find a negative number. There's a lot of outer here, but everything that's not outer hopefully should make sense, right? We have a vector, we pass it to find if, we check if we check that x is less than 0, right? What's interesting here is that we pass a vector inside our algorithm and not a pair of iterators. All of our algorithms are range-based because sometimes a range can have more information attached to it than a plain pair of iterators. Like, let's say we can know that the underlying data is aligned, right? And if we look at the assembly here, right, this is vectorized. In fact, this is very similar to what benchmarks which Joel showed you at the beginning. Okay. Let's put the auto in place, right? If I open next slide. Okay, so we will return the const iterator as you would expect. Internally, we will go to pointers because we can't really do any SIMD on the iterators, but we will just convert the output for convenience type, the one you would expect. A second interesting aspect here is this predicate. Right? Usually when people write SIMD, they will have the main part written with SIMD instructions, and then they have a scalar cleanup at the end or at the beginning. That sometimes is known as loop peeling. However, we find that if you do loop peeling, it is very difficult to write predicates. You have to make predicates that works both for scalar code, for SIMD code, and that's not very pleasant. So we use alternative techniques to do the tail cleanup. I'll show you how we do it. And all of our algorithms are always accepting a wide register, right? Second interesting thing here is, which is typical for libraries like this, that operator is overloaded to return you not one Boolean, but a vector of Boolean values, right? So this on my machine will be, for example, 8 Boolean-like values. Okay, the last interesting thing here is if we look at the assembly again, right, we will see, we load from 4 addresses. In fact, this is because we do unrolling for you. Find if, because it's a simple algorithm, massively benefits from unrolling. However, what if your predicate is pretty complicated? Like this is something, this is a bit of an artificial example, but we take a floating point number, we convert it to a rational number, and then we return if the denominator is bigger than 7. I'm not sure there's a use case for it, but the point is it's a complicated predicate, right? And if we look at the assembly, we will see about, a lot of instructions. However, we're probably not benefiting from neither unrolling, or we will align all of the loads for you. This is probably not going to matter anyways. So all of the algorithms in if support certain settings that we can do. We can, for example, do if algo, unroll 1, right? And then if algo, no aligning, right? And if I open the results for you, as soon as it compiles, it will be 180 instructions, right? There was more than 500 before, and presumably it will be about the same speed. Okay. So with this, hopefully, find if makes sense. Let's look at the next one. Let's look at mismatch, right? Mismatch will, give it 2 ranges, right? And finds you a pair of elements in parallel ranges that are not equal to each other, right? With a custom equal predicate. Well, in the standard library, if you look at mismatch, it will have a separate loop, right? So somebody will write a separate loop to do that mismatch. But for SIMD, even the simple act of writing a loop is pretty complicated. And we all really wanted for mismatch to just call find. How do we do this? All right, so imagine we have 2 arrays for simplicity of integers, right? So this is first array. We have a first pointer pointing here, second iterator pointing here, right? At this point, we can write our algorithm. We can load a vector from each of one of those and do comparisons, but that requires writing a separate loop. So instead, we introduce an abstraction that you may be familiar with from ranges v3 of Python called zip, right? And so when you read from the zip, you get both of these registers in one object. And then we can do find on this zip. Okay. And in fact, we call this object also wide, only of tuple int. Kumi is our tuple library that is better than the standard one for various reasons. Why do we call this wide, the same as for register? Well, because it actually has a lot of the same properties and has a lot of the same behaviors. We can compare those for equality. It makes sense. It works. We can move elements around, pretending the element is a pair of integers, and it also works. Okay. So because we have the zip abstraction, our interface to Mismatch looks slightly different from the standard one, right? So standard one looks like this. You have the first range, right? Iterated to the beginning of the second range, and it returns you a pair. Well, we have a zip iterator that is a much better abstraction than a pair of two iterators, right? Here we accept two things that zip to range together. As I mentioned, we are range-based. So we will get two things that zip to range, and that means we're slightly more flexible than the standard. For example, you can give us a range and an iterator, and it's okay as the standard. You can give us an iterator and a range. That's also fine. Or you can give us two ranges, assuming they're the same size. Like you cannot zip two ranges of different sizes. And finally, it turns out to be very beneficial to have a version that accepts a range already pre-zipped. I'll show you actually an example right now. When we're going to write a memcmp using if, right? So this is standard memcmp. First thing we'll need to do is we'll need to convert all the void stars to something we can work with. In my case, it's going to be pointers to uint8, right? I'm going to create the first range out of first two pointers, as range is an abstraction we provide to do it. I'm going to zip it with the second iterator, get the zip range, and then I'm going to call mismatch. When I find the element, like same as the standard, if it's the end, we return 0. There is no difference was found. Okay. And here we do the, memcmp has to return a negative number if the first one is less, a positive number if the second one is less. This is the code, right? An interesting thing here is this if read. If you're familiar, for example, with ranges with free zip or something like that, they use operator star to get two elements of zip, as well as all the other iterators. However, that implies using proxy references. And proxy references are really problematic to work with. In our case, because we only deal with plain old data types, we can just do if read and if write, and it just works, and it doesn't involve those unpleasantness. Finally, well, let's say if I'm going to scroll down a little bit and a little bit more. Yes, this is the main loop. And this main loop will look a lot like to what you will find in, let's say, glibc main loop of memcmp. So you get the same quality of code. In this example, we use zip for the same type. But what we want to zip for different types? It's actually okay, just works. The way it works is we have the same abstraction wide of tuple, only I can have different sizes of types, like let's say int and double. And under the hood, for a smaller type, it will use a small register. So for example, on my machine, I have a 32-byte register that I will use for double. And I will use a 16-byte register for int, because int is half the size of a double, and it just works. In fact, the zip is very powerful. It is, you can pass it to any algorithm. And so for example, using zip, we can write an inclusive scan of complex numbers. Right? We have a real part in a vector float. We have an imaginary part in a vector float. We zip them together, define a plus operation, and call inclusive scan. It works, right? An interesting thing here is this, how we pass an operation. So instead of an operation being passed, just operation being passed like in a standard inclusive scan, we pass a pair of operation and an identity element for that operation, right? So if you call plus with this element, we'll get the same result. This is kind of just how the algorithm is implemented as a code. It needs that information, right? The second interesting thing here is that if you do, this is 0, and 0 is a little bit special. So for example, right now, it's about 230 instructions. If I pass a special tag type called if0, right, it will become 211 instructions because the main loop became slightly more efficient, slightly smaller. And stuff. Okay. The last thing I'm going to show you before I give you back to Joel is this collect indices example. This is a real example that was provided to me by Max de Marcy, who has this project called RageDB, right? And he wrote to me and asked, hey, Dennis, I'm looking to use SIMD to optimize some code. And the problem looks like this. We have a vector of elements and we have a predicate. And I want to collect indexes of all of the elements that match the predicate. Well, the first reaction I gave him was the same reaction you get when you ask anything on the internet. How do I do X? Don't do X, right? Which I had my reasons, right? First of all, like indexes, what's your index type usually? Well, usually it's 64 bits. So it really limits how wide of how many elements in one go can you use, right? Because I can do, for example, 8 32-bit elements and only 4 64-bit elements. Second reason is more fundamental. That, okay, you collected the indexes in the vector. Presumably, you want to get the elements back at some point. How do you get the elements? Well, probably not with SIMD, because SIMD really likes the data to be contiguous. I mean, there are instructions to do it, to load SIMD register from multiple places, but I have no idea how efficient they are, to be honest. But anyways, he asked for it, so I wrote him an example, and he claims that he managed to speed up the request per second about 5 times. Okay, the fundamental building block we'll need is a fundamental building block of remove. It's called compressstore. What's the idea? You pass it 3 parameters. You have a register, you have a mask, and you have a pointer where you want to write values. What it will do, it will write all of the values marked as true in the mask, and then it will return you where it stopped. It's kind of like a remove, only for a single register. Now, it has an unsafe modifier. Why? Because I can make it more efficient if I write a little bit extra on the end. Okay, so now let's build an algorithm using this. This is a little bit of an interface. This is going to be our interface. We're going to accept a range. This is our range concept. It's slightly different from the standard one, but anything that is a vector will work. A zip range will work. Then we accept a predicate and we accept an output parameter of a vector, right? The reason I'm using output parameter is I mentioned that I want an index type, right? So for example, if you know that your indexes are 32-bit, we can be more efficient. And second, I didn't want to deal with allocators, so just give me a resulting vector. Okay, we're going to assert that every index can be represented as the index. This is just an index type. This is just a precondition of the algorithm. Clear the input. If the range is empty, we're going to return. The reason this is important is because usually this is a stylistic thing, but we will do different things. Like, for example, we will memcpi, and memcpi requires you to have non-null pointers. And if you have, like begin and end can be null pointer, right? Even for 0 bytes, you have to memcpi from a non-null pointer. Okay. Now, we need to convert from the input range to something that is easier to work with. This is a function to do that called preprocess range, right? I will tell it to consider the index type when it's going to select the widths and all of the other stuff. Why? Because we really don't want to have, let's say, try to use 64-bit elements, index elements when I have 64 chars. We just don't have the registers. So it's better if the library knows about the index type and will select a smaller, more appropriate size, right? We're going to get the register, iterators. We're going to get how many elements it wants us to go in one go. At this point, I usually just go for each and call it a day. But I want to show you there is nothing up my sleeves, right? So let's see how the loop actually looks like. So we're going to over-allocate our output vector a little bit because we want to always use on safe store and never have to deal with, masking writing. Now, imagine that you were doing this in scalar, right? You would have something like for I equals 0, I not equal size plus I. In SIMD, we do the same thing, except instead of having one I, we're going to have a wide I, right? Assuming that n is 4, it's going to be something like 0, 1, 2, 3, right? Next iteration plus 4, it's going to be 4, 5, 6, 7, right? This is our wide I. Okay, so main loop. While we can do the complete register, load, apply the predicate, do the compress store, increase the iterators. Makes perfect sense. Clean up, right? Let's assume we had 4 registers, 4 elements in the register. We had 3 elements left. Okay. We have this abstraction called ignore, right? Well, there are a bunch of them, but this one is. We're going to create this keep first 3 elements. What it will do is when we apply it to load, when we load first, the first 3 elements will be okay, and the last element will be garbage. We don't know what it is, but it's safe to do that, like it will do the appropriate masking. Now, we apply the predicate. So first 3 elements are okay. The last may be true, maybe false. We don't know what the result of applying predicate to garbage is. We need to mask it out. This is the syntax to mask out that garbage from the end. And then we're going to do a compressed store, same as before. And finally, we're going to do, we're going to shrink the output vectors. There was a little bit of maybe nonsense in the end. And we're going to shrink to fit just to remove extra allocation. And that's it. And if we look here, we can see that we're loading the patterns and doing shuffles. Okay, and with this, I'm going to give the word back to Joel as soon as I figure out how.
And I'm back normally? Yes, it is. So thanks, Denis, for this. I want to quickly show you last things that go with our algorithmic support. So let's go back for a while to the inclusive scan of complex number example. It's all fine and dandy, except we have to handle those get to get the smallest, the internal parts of the registers to do the work. And we were feeling uncomfortable to get people having to manually do those tuple-like operation. So what we wanted to do is, how can I write actual SIMD code using actual data structures and it doesn't look like I'm actually doing crap? So let's have a look at that. So let's write a piece of code that actually defines complex structures using our struct supports helper that will do some CRTP magic. And we give you an internal state made of 2 floats. That's what we want. We do this small friend function, re and m, that will get you the real and imaginary part of the complex. And to do so in a cool way, we have this like concept that lets you say, I want to take any parameters as long as it looks like a CMPLX. So either an actual CMPLX instance or a wide of CMPLX. And in both cases, we do the same thing. We extract the proper part of the underlying tuple. By actually inheriting from struct support, we get a lot of operators for free, comparison, equality and inequality, and we got ordering, and we got the potential for all the numerical operators like plus, minus, and so on. And I will explain that later. But of course, if I'm dealing with complex, I need to opt out from the ordering, so we can just shove this type dev there to say I don't want ordering by default. Thank you very much. And as I say, we have the potential for getting numerical operations, and the numerical operators appears at the complex and wide of complex level as soon as we define the compound operators associated to it. So as soon as you have plus equal or minus equal and so on, all the related operators will kick in. So what we do there, we got the self, we got the other vector, we got the other complex, we do the operation and so on. You can do the same for a unary operation like minus and minus equal. And for optimization purpose, you have to do minus equal if you want minus. We don't do minus doing plus and unary minus. So you can do that for all the operator you want. So we stop there. You can also, if you have a stream insertion operator, we can reuse it to display the vector of complex. And we have this tag dispatch system that can let you say, I want to override the behavior of a given AU function for this type, and I want to do that instead. So for example, there, for the absolute value of a complex number, I want to compute the modulus. So I will just take complex when I'm calling apps, getting the subparts and calling the iPod functions. And so we have this structure of complex, which is actually compatible with vectorization through while. And next, what we wanted to have is, instead of having a pair of a bundle of vector of whatever, what about having an actual container for such vectorizable structure? And that's what SOA vector does. It's basically the same interface as vector, except it awaits if compatible structures, and it will take care of all the array of structure to structure of array conversions. And then it also supports all the classical range interface, so you can actually directly put it into inclusive scan, for example. And the code is actually slightly better because SOA vector knows that everything has to be aligned, everything is properly set up, it's allocated, so it doesn't have to do any special things. So the code generated is actually better than the one before. And then it gets enrolled and so on and so forth, and everything just works. So you can actually define your vectorizable structures this way. There is also another way to do it, which is actually just overriding threads outside of your type. If you want to adapt a pre-existing types, it's also supported. And once you do that, you can actually do actual data-oriented design. So let's say I want to do some physics. I have a bunch of balls that bounce over the z-axis, and I want to do that somehow properly. So let's say your ball, you have a ball has a position of a z, a speed, it has an elasticity value, how much is it's bounced for, and it has a counter, which is an integer of how many times it bounced. So we get that, we get the struct support for there, and we can make a small simulation step objects that say, okay, I'm taking a ball in, I'm computing the gravity things over the falling ball, okay, and I'm updating the speed and the position accordingly. And I have another ball, which I call bounce, which computes the state of a ball whenever you're whenever it bounces, we compute the state of the bouncing ball. Why are we computing both? Because in SIMD, you don't do branches, you do selections. And so we have this if-else operation that let you select between the bounce and falling states. And we consider that if I'm very, very close to the ground, I'm bouncing. And so we can actually take a bunch of balls in the SOA vectors. We do the transform to transform the ball states, okay? And what we do is that we can use classical idioms like erase remove by, let's say, okay, let's remove all the balls that bounce more than a given times and erase them again. And we got some kind of nicely laid out main loop. So here it is. So we have all the add sub null from the physics, we have the blend from the selection, and everything is done twice because it's annulled twice. So we are at the point where we could actually write high-level struct-based operation and algorithms, and they get vectorized. And on the user side, there is no trace of actual intrinsics. Okay, so what if you actually want to play with that? I mean, how does it work? So a bunch of practicalities. The first question is, what about bugs? What happens if I try to make this work and it doesn't work? Well, yeah, there will probably be bugs. Like Denis likes to say, the API surface of Eve is basically the size of the moon or Mars. So we may have missed an interaction. So don't hesitate. Write your code, do some tests, benchmark, and if something fishy comes out, just ping us. What about API stability? We are still in a place where we want to break things, so no API stability for now. Most of the API is basically set because such choices that were made long ago and they are proved to be good. But there is a bunch of stuff we may want to change, especially on the wide interface. We are using tag release, so if you want to stick to something, you can actually know where you should stop updating. But currently, we are still working. So what if you really want to do that after all these things? Well, try to focus on your critical components in terms of speed. That's the important part. Can actually try to build a standalone library, either dynamic or static, so you can extract your kernels into something that you can manage on the side and call them from the main application. It helps also if you do dynamic linking with those library, you can actually handle the cases of you know that you want to support SSE2 and AVX and AVX2, but you don't know what your user will have, so you can actually compile multiple times the same kernel with different options, and then you dynamically load the correct one if provide a runtime system to detect at runtime instead of compile time which kind of SIMD instruction set is available. And of course, well, you can contact us. We will be very pleased to help you getting started. There is a bunch of similar library, as some question already mentioned. The most well-known is probably VC, which is slated to be somehow standardized. So SIMD, TSIMD, insert a random consonant SIMD. There's a bunch of them. To the best of our knowledge, we are the only ones that actually provide this algorithmic block of codes and the ability to work properly with structures. That's our main differentiation points. Most of them are really cool. They do a great work actually wrapping things, but we go the extra mile. You also get, you also have, oh, sorry, it doesn't work. SIMD everywhere, which is a different approach. It will just fill the gap between missing and 26. So you can write code that works on any kind of instruction set and we just emulate the missing operations. It's a different use case. Mostly you were forced somehow to write SSE2 code at some point because you don't know why. And then you need to migrate elsewhere. It's helpful for this kind of thing. But it won't go further than that. Mentions before we close. So special thanks to Jean-Thierry Lapreste, which is our third co-author for the library. He does the math and a lot. He likes that. So most of our numerical algorithms are actually coming from him. So a big thanks to Jean-Thierry. A bunch of shout out to a bunch of people over Stack Overflow in no specific orders. Peter Cordes, Zibozan, Akrit, Stephen Cannon, which all help us maxing this idea about how to write proper algorithms. The SR vector ideas come from Unity. That's something we find quite interesting, so we just run with it. If you want to see other talks, Denis made a talk some time ago about using Eve from scratch. Again, you can follow the link. And this is our contact. You can find us on Discord. We have our own Discord. We are on the hashtag input Discord. We are on CPC Slack. Fire us an email or get us on Twitter, and we'll be very happy to answer your questions. So thanks for your attention. I think we have like 5 minutes for questions, I guess. So I can actually maybe answer some of them, and we will be probably finishing that later on the gather. Okay. What about, okay. Yeah, I think I answered the first one about difference between our library and the other one. Again, the main part is that we have basically what they have and then some. Okay, we also one of the few that have something more than x86 because we have the ARM and the upcoming PowerPC supports. We have this question about why do I wrap the function instead of the argument in the quarter cycle example? And it actually goes hand in hand with the question about how we implement math functions. The story goes this way, actually. Math functions are usually approximation, as you say, Alexander. And you have to choose how far you go deep into the approximation or how low you go because you want to go faster. So our stance on that is that the main function, let's say, I don't know, log, let's take log for an example. are basically the basic cases you can write and get decent results for most, let's say, normal input, like no nans or no env or no whatever. And you can actually write a more pedantic version that will go slower and take more case into account. Or you could have a very rough version that go faster because it just do a less profound approximation. Same goes for a lot of things. What we do is we have this decorator system that does that wraps the function with an extra semantic. So we have a bunch of them. The four main ones are the raw one that just say, I don't care about special cases and whatnot. I just want to go fast. You have the pedantic one that adds more checks. We have the numeric one that basically says that you are only dealing with numeric values, so no env, no nan, no whatever. And we have the full one, which was the full one already. We have the regular one, which just do the same what the function does already, but it's also a decorator for homogeneity issues. And when we were looking at how to make trigonometric faster in some cases, as we already have the system for doing this decoration on object, what we decided to do is actually do the same thing. I don't really like the fact that we wrapping the value into stuff because it makes the mapping of the concept a bit more complicated because you have to care for float and float wrapped in whatever, and it's easier for us to do the other way around. The other one are probably a bit more complicated.
This is about Clang GCC extensions. People ask.
You want to answer that or?
I can. So the Clang GCC extensions depends on what you want. We looked at built-in shuffle, which would be really nice. But the problem is built-in shuffle doesn't do all of the cases, and so we decided we're going to have our own shuffle compiler. And they also it doesn't do MSVC. We would like to do MSVC essentially. What else? Support for all platforms. They're not like SIMD code. A lot of SIMD code is like about doing crazy optimizations. It's like spending a lot of time on a single instruction, and I don't see how specifically Clang GCC extensions would be sufficient for that. Right? You need the intrinsics. Anything you do needs the intrinsics, maybe. What we do on V7, we will do WASM in some near future. It's just WASM is experimental now, and we are a bit scared of the experimental stuff because there's a lot of rework. There's a constant evaluated question. No.
I don't think we will because every function in Eve has a scalar version, so we could actually say that the scalar one is actually constexfer in some cases. The issue is sometimes we will end up having to call std mat functions, and none of them are actually standardized to be constexfer, and that's a bit iffy to do so. For me, it's another library, actually.
There's a compress question. Do the
compress.
And it will take me hours to explain the compress. So very quickly, there is, a crate person that we mentioned came with a solution with 27 masks. So you store 27 masks, and with 27 masks, you can do a compress on 8 elements. And that works on SSE3 and up. For SSE2, we do a switch table, which is not too bad, but kind of for IDX2, you can also use BMI instructions, which is like compress extensions that you mentioned, but on 8 bytes. But that only works well on Intel, doesn't work well on AMD. So we are going to do that on some IDX, when we know it's not AMD. Come find me later. I'm happy to talk your ears off about compress.
The SVO1, and probably we need to stop.
I don't know. Yeah, I think we need to stop already.
We need to stop already. Okay, so I don't know, Joshua, should we stop? Okay, fine. Okay, so thanks to everybody. Stanislaw, don't hesitate, and Alexander, don't hesitate to come on together. We'll be happy to, and other people, we'll be happy to chat about the remaining question. Thanks again for your attention, and have a good day.